Hello, this is Aaron from ToolChef. In this video, I'm gonna introduce the new feature and changes to the AtomsUnreal 3. So let's start with the agent group, and let's start with the skeletal mesh component and the new agent type component. Here I have a simple example with some agents. As you can see, there are two components here. One is the man, that is the new agent type component, and then there is the skeletal mesh component here. We added this new agent type component because this component contains the poses of all the agents are using this agent type. So instead to have the pose on every skeletal mesh, how it happens in the previous version, now it just saves just one time, and then it will handle all his children. So it will handle all the skeletal mesh component that compose basically this agent type. Or if you have variation, you have the multiple skeletal mesh component that are used by this agent type for each variation. So this is more efficient, also it's faster to compute and to draw compared to the previous version, where on the previous version basically you had just the list of all the skeletal mesh. So for example, if we take the variation example, you see there are also there is a list of all the skeletal mesh component. Also here it's using a specific name like the agent type, variation, and mesh name. Also you see there is in the previous version there is this _a. It means that these components are automatically created and you can't modify. So if for example I try to modify here the material or other parameter, this will be overwritten every time. To be able to basically handle this one, you just need to remove the underscore here. With the new version, there is no such thing. So you have the skeletal mesh component, you can add manually this component. As soon as this one is added as a children to the agent type, then you can edit. So for example, you can change the material. Let's put the material here, and as you see, it automatically updates. Also, it takes the changes here. Usually, when this component is created by the agent group automatically, so it takes all the property for lighting and rendering from the agent group as default value. So if you want, you can change here, and all the skeletal mesh component, when it is created, it takes that default value. But as soon as it's created, then you can change and set any value you want here. So it's more easy to handle. Let's have a look to the variation. Let me add some variation here. Sorry, yeah, and let me assign some variation. Okay, so let's have a look here. So now you see there are more skeletal mesh components because I have different skeletal mesh in here that compose this variation. As you see, the name conversion is changed here. There was the agent type, variation, and skeletal mesh component with material. With this old version means that the same skeletal mesh, if it was used by multiple variation, then you had basically you could have multiple skeletal mesh component here that was using the same skeletal mesh. With the new version, all this stuff are gone, and now it just creates one single skeletal mesh component for each geo basically. And so even if this geo is used by multiple variation, then there is only one skeletal mesh component here. Let's have a look to some parameter here of the agent type component. So probably there are a couple of parameters that you usually want to handle. So one is the number of lots. So as I told you before, basically all the poses are stored inside the agent type, and then the agent poses are used by all those skeletal mesh components. It means that this agent type also basically handle all those components, and it will handle also the lot selection. For this reason here you see this numLots property. So if you have skeletal mesh components that are more than 4 lots, for example, if you have 6 lots, you can put 6 one, and then basically all the skeletal mesh component has use at least 6 slots. Obviously, if your skeletal mesh has fewer lots, it will just use the lots that it has. And here, let me put back the 4. Then here you can stop the minimum lots. Now let's have a look to the bounds. So usually during the simulation, Atoms compute automatically the bounds based on the agent's bounds. Here you can see you can save sometimes, especially if you have agents that are in idle, so they don't move too much from their start position, for example in a stadium or wherever. Then you can set up a static bounding box. You can just turn on here and then set the parameter that you want here, and then basically you set your static bounding box. In this way the agent group doesn't compute the agent bounding box at each tick, but just use straight the static bounding box. Okay, let me turn off this one and I show you how you can generate variation at runtime, adding skeletal mesh component here. So let me turn off the bounds. Let me turn off the variations. And let me remove. Okay. So in the previous version you need to basically prepare all the variation in advance as assets. So you add the variation table here with for each agent type. You add the list of all the variations, and the variation basically each variation is a list of skeletal mesh. So now basically you can add skeletal mesh component at runtime and add the agent that you want to the list of agents that a skeletal mesh component draw. You can do in blueprint. It's pretty simple. What you need to do basically, for example, let's okay here, so we can get component by class. Let's take the agent type component. Okay, the agent type has some methods. For example, we have the add skeletal mesh instance component or attachment, and here we can add a new skeletal mesh instance component with a specific skeletal mesh. Here, I don't know, let's take issues here. Okay, this one return the new skeletal mesh component, and then at this point you can add a specific agent to the list of agents that this component draw. Here we can get the group ID. And here we, sorry, not here on the agent type, where the add agent skeletal mesh instance. So let's get here. Here we pass the skeletal component, and then here we pass the agent group there. Obviously, you can also remove agents from a skeletal mesh component. There are just the remove agent from skeletal mesh mesh instance component. So if I compile and press play, now you see there are also the other shoes that we just started, and also there is the skeletal mesh component that we have touched. Obviously, in this case, we would like to remove the old shoes, but in this case, we have just the default skeletal mesh. So if we have the other full variation, you can just remove. In this way, you can build variation at runtime. You don't need to build all the variation asset if you want. Let's have a quick look to the attachments. So I have my main agent type variation. The setup is the same of the previous version. Here you have the bone name, put left hand, for example. You have the offset and the static mesh. Here, let's scale a bit and let's save. Apply the bind offset. So the setup is the same. What is changed is the component that is using this attachment. Before it was using the static mesh instance component. Now there is this new skeletal attachment instance component that basically is almost the same of the skeletal mesh instance component, but instead taking a skeletal mesh as input, taking a static mesh. And then you have the usual parameter here for lighting, rendering, and so on. So it's just that it's faster compared to the static mesh instance component. It also can be used with the XPU simulation that I'll show you in a bit. Now let's have a look to some of the new parameters on the agent group actor. So let's start with the simulate only visible agents. This one has the previous version. If enabled, tell Atoms to simulate only the agents are inside the frustum at a certain distance from the camera or with a minimum screen height. The new option here, check static bounding box, that as I told you before, the agent type can be set up with a static bounds and instead to compute every time. And here, if you turn on this option, it will basically use that global bounding box to know if Atoms need to disable completely the simulation on agent group or disable the agents. So if you are using the static bounding box, and if you want to turn off the simulation, the agents are not visible, you can turn on this option, and Atoms will take less time to check if you need to completely disable an agent group. Let me remove this one. The other parameters here are the same. We did some changes to the KD3 computation. Here you have the usual enable neighbors query. So when you turn on this one, at every tick, Atoms update the internal KD3 that store the position of each agent for a fast query. We had another option that is the enable internal KD3 cache. This if you turn on, basically Atoms compute just one time the KD3 the beginning of the simulation, and then during the simulation it will not update anymore. This is useful, for example, if you have agents that are idle, so they don't move too much from their position, for example in a stadium. And this one can increase the performance if you need to query the neighbors during the simulation. All the other parameters here are the same for the per instance metadata, also for the hero promotion. Another feature that is in AtomsUnreal 3 is the new initialize agents with metadata method on the agent group. So the agent group now has this initialize new agent with metadata. So you can initialize a new agent, but also passing some custom metadata. So instead to basically add metadata behavior component here, or adding metadata from the behavior tree, you can just fill up a map metadata here. Here, and then you can add metadata here, like set double metadata through its value, and then basically just passing this metadata here, and then you have all the other parameters like position, direction, scale, gen type, and group ID, and so on. Now let's have a look to the new hero promotion workflow. So the standard workflow is still here. So you can basically promote agents using metadata, or just promote all the agents. You can do runtime, you can promote or remove agents. For example, here, if we turn off the promote all agents, you will see basically that each agent then is using its own possible mesh component here. What we added basically in the new version is the custom hero workflow. So let me remove this one. And let me open this example scene. So on the agent type, we have this new option. Sorry, on the agent type component, we have this new option, the use custom hero promotion. If you turn on this property, then when agent is promoted by the agent group, it will call this basically event. So it will not generate anymore the possible mesh component for this agent. It just calls this event. At this point, then you can basically do your custom promotion. In this case, basically, I'm instancing this character that also is using new anim blueprint nodes that we added to the new version that can use basically to read the pose from an agent, and then basically setting on the character. So let's have a look. For example, this setup. So I have here, in this case, I have these meta-humans, and I've created this anim blueprint. Now there is this Atoms agent pose new nodes here that you can use basically to read a pose from an agent, and then setting the pose here in the anim graph. What you need to provide basically is the agent group and the agent ID. In this case, for my promotion, basically I'm getting the agent group and group ID from the onHero agent created events, and spawn the character here, passing the agent group and the agent ID. So then this way the character class can use those data inside the anim blueprint. Then there is also the remove event here that just, in this case, removed the character that I created, destroying the actor. Also here I have this other setup that basically I'm saving my new character as a object metadata on the agent, because later in this way I know which character is using basically that agents, and then I can get back the actor and then destroy the actor. So let's press play here. So now basically you see there is the BP Daniel, that is the character, and here basically it's removed and then added. In this way you can customize your hero promotion, and if you need, so for example, cloth simulation or or the full character, you can use it and have a full character as a hero. Now let me introduce the animation XPU features. This is the big new feature that you have in AtomsUnreal 3, and that really push a lot the performance. So usually with a standard setup you add some grid layout, for example, to generate some agent, then you have the state machine. If I generate a lot of agents here, for example, and then I simulate here, basically the pose is computed on the CPU, and then the GPU just do the instancing and the skinning. So if I check the stats, here you see the game takes, for example, 13 milliseconds. Also if I check the Atom stats, it's taking basically 7 milliseconds here. And now it's running on 70 FPS. So we added some new components. So instead the state machine behavior, let me add a state machine XPU behavior. So now let's press play. Now basically you see the game now is 7 milliseconds, and also the FPS now is 120. So what the XPU does, basically with the animation XPU we split the computation, the pose between the CPU and the GPU. So on the CPU we just compute the root motion, and this way we are able to access all the for example the navigation mesh, we can access physics, we can simulate a capsule, for example. So it's like basically it's like before. So we have the root, also we have the ground adaptation, while the rest of the pose of the agent is computed basically on the GPU. For this reason it's a lot faster compared to the standard state machine. If we profile the GPU, we will see that here there is this new Atoms XPU category, and this one is my agent group, and then there is the compute shader that compute basically the pose and do the animation blending. The asset setup is the same, so you don't need to set or bake like texture when usually do with the vertex, for example with vertex animation. You just need to set up the standard state machine, in this case the state machine, and Atoms will use the state machine, will upload the animation clip on the GPU, and then we'll use those data to compute the pose of the agents. So it's really straightforward to move to the XPU setup, and you don't need to bake anything basically. Also the speed, as you can see, it changes quite dramatically. Obviously there are some limitation at the moment. So for the state machine setup, here in each state you can have multiple clips, but all the clips must be in random mode. So it doesn't support anymore. Sorry, it doesn't support at the moment the merge type, the merge type as merge. Here also the additive clips is not supported at the moment. But if you have multiple clips that you want to randomly play, that all works. Also the transition works fine, so it's basically just that for the state machine setup. Then for the ground adaptation, at the moment Atoms is able to adapt the pelvis to the ground, but not the feet. So there are a couple of limitations. Also, since the pose is on the GPU now, all the nodes like the get joint transform, joint matrix, or doesn't work, because on the CPU there is just the root joints. But there are basically methods to compute the full pose on the CPU if you need it. Also, for this reason, you are able to export a Atoms cache or a USD cache from an XPU setup, because when it's exporting, basically it requesting the full pose for each agent, and the state machine XPU will compute the full pose and return to the cache exporter. So you can still export a cache from here. Now, as I told you before, basically some of the full pose is not on the agents. It's not on the CPU. So, for example, the joint transform behavior or joint aim doesn't work. You need to use the proper, basically, XPU behavior. For example, the joint line, you have the XPU behavior. The same things is valid for the behavior tree. So, for example, on the behavior tree, there are new tasks that are specific for the XPU. So you have the joint transform XPU, joint align, joint aim. So if you need to align, aim, transform some bones, you can do with the behavior tree using those tasks. We have also the play animation XPU. So the play animation, just basically play an animation, is the equivalent of the play animation task, but this instead will run on the XPU. If you want, for example, set up a single behavior tree that run for XPU and the not XPU setup, you can use the agent as metadata, for example, and checking for the XPU metadata. Or the agents that as XPU setup have this metadata. So you can use this one to basically switch from one setup to another. For example, on this setup, this behavior tree, the basically just a simple example of a play animation, also a joint transform here. So the joint transform is adding some offset to the left shoulder, and then this play animation that is playing is playing this asset, and then you can see the joint transform that's applied to the shoulder, and then the play animation. If you want, you can run the play animation not just from the behavior tree, but there is some new methods on the agent group. So there is this play animation XPU. That they can use basically to play an animation outside the behavior tree, for example, if you don't want to use the behavior tree. One important thing about the play animation XPU task and method here is that all the anim sequences that you are going to use must be somewhere inside the state machine. So if we have the state machine here, even if they are separate state, not connected to anything, but it's important that all the anime sequence that you are going to use on your agents are here, because the XPU, the state machine XPU, loads on the GPU all the animation, all the anime sequence that is found here on the state machine. And the play animation, for example, is requesting to play a specific clip, and since only the anime sequence that are inside the state machine are loaded to the GPU, you need to basically set up all the anime sequence here. Even if you are not triggered the state, for example, you can do some dummy state here and then add the clips here, are fine, but it's important that all your anime sequence are inside the state machine, so the state machine XPU can load them on the GPU.